Hey, welcome back everyone. Today I'm going to be taking a look at plotting pixels and changing color attributes on the ULA screen for the ZX Spectrum Next. And in order to understand the material being covered in today's video, you should probably be already familiar with how the display works on the regular Sinclair Spectrum computer, which is the display memory, and how the ULA, which is the uncommitted logic array chip, automatically plots the graphics onto the screen, as well as you should be familiar with the color attributes and how they work with the screen as well. Because I won't be going into too much detailed explanation of exactly how the screen is laid out, but we will be looking at it a little bit, so there'll be just a brief introduction to that. But if you're not already familiar with how the graphics and color attributes are displayed on a regular Spectrum screen, you may want to brush up on that before checking out this video. But otherwise, you can just tag along and see if it makes sense to you. Although I'm pretty sure probably most of you are already familiar with how the display and the attributes memory works on a regular Sinclair Spectrum computer, which might have you wondering, well, what's the big deal about displaying graphics, pixels, and color attributes on the ZX Spectrum Next ULA screen? Doesn't it work the same way? Well, that's what I assumed as well, but it turns out that it doesn't necessarily work exactly the same way. And I'll just show you a sample program today just so we can go over it, and you can follow along with me if you want. If you haven't already tried doing this on a ZX Spectrum Next computer, then there's just one thing we need to watch out for, but we'll also learn one or two new techniques along the way. So we'll take a look at my program here and we'll see exactly what we're trying to do. Okay, so let's take a look at my screen now. And you can see here I've just got a couple comments at the top of my program that indicate what the program is supposed to do, as well as a note. And let's read the first line here that says, "This program plots a byte of pixels to the ULA screen." So if you're not already familiar with the ULA screen and exactly what that means, the ULA is a chip or an integrated circuit, an electronic component that is inside a regular Sinclair Spectrum computer. And one of its jobs is to display both pixels and colors to the screen. And the way it does that is it looks in certain memory locations that have been reserved to store pixel data as well as color attribute data, and it just simply automatically transfers those values directly to the screen. And we'll take a look at a bit more detail how that works in just a little while. But basically what this program is going to do is all we want to do is simply plot 1 byte of pixels to the first location in the display attribute memory, which is the top left-hand corner of the screen. And I'll just show you an image of the pattern that we want to plot to the screen. It should look like this. So every alternate pixel in a single 8-byte pattern should be turned on. And so we should end up with a blank screen that has just these 4 pixels turned on in the top left-hand corner of the screen, which is what you would expect if you simply stored a value that equates to these pixels in the ULA memory or the display memory of the computer. And that is how it works in a regular Sinclair Spectrum computer. And just to show you how that works on a regular Sinclair Spectrum computer, just in case you're not already familiar with it, I'll just bring up my ZX Spin emulator just quickly and we'll take a look at that. Alright, so here I have my ZX Spin emulator and assembler on the screen, and we'll just see how we would want to plot this pattern to the screen on a regular Sinclair Spectrum computer first of all. So first I'll enter an org statement, let's say 30,000, and then I'm going to load this value into the A register that represents this pattern of pixels for the byte we want to plot to the screen. So here I'm just going to load a value into the A register that represents the pattern of pixels that we want to plot to the screen. And you can see I've used a formula here where each value that I'm adding represents one of those pixels according to the diagram that I'm showing. And now we want to load that value into the first memory location of the display memory, which is address hexadecimal 4000. So I'll just load that into the HL register first of all. And now I want to load that pattern of pixels, which is stored in the A register, into that memory location. and then finally my return statement, just like that. So now this program should store a value that represents these pixels into the A register, and then store that A register value into the memory location 4000 hexadecimal, which is the first memory location of the display memory. And as soon as that value gets stored, the ULA chip inside the computer will automatically display that pattern to the screen. And that should be located in the top left-hand corner of our emulator. So let's go ahead and assemble this program. And now go to our emulator and we'll run it by typing randomize user 30,000, and let's see what happens. There you go. We now have a pattern of pixels plotted on the screen, and all we had to do to accomplish that was simply store a value into a memory location that corresponded to a location in the display memory. In this case, the first location in the display memory. So that's pretty simple. Now let's see how we do that on the ZX Spectrum Next computer. Alright, so I'm back in my Visual Studio Code editor now, and this program contains some extra code that we're going to be looking at in a moment. But first, let's take a look at the top part here, where I have the main program loop, which is right here after this start label. And what this main program loop does is it calls three subroutines, sub1, sub2, and sub3. And then finally, it just has an endless loop here at the end where it has a jump $, which makes the program jump continuously to the same program counter location, which corresponds to the address where this jump instruction is located. So you can see now I've commented out these first two instructions of call sub1 and call sub2. And all this program is going to do right now is call one subroutine right here, sub3. So let's go down and take a look at sub3 and see what it is supposed to do. Alright, so this program should look a bit familiar to us now because we just did exactly the same thing in this ZX Spin emulator, but now we're going to be using the C-Spect emulator, which is designed to emulate the ZX Spectrum Next computer. And let's see what we're doing here. So here's sub3 here, and the comment says plot byte value to screen by loading display memory, which is what we just did using our ZX Spin emulator. So in our first line here, it loads a value into the HL register pair of 4000, which is the start of the display memory, which is the top left corner, as we just tried out, and as is indicated by my comment here. And then in our next instruction, we're loading that same value into the A register again, 1 plus 4 plus 16 plus 64, which represents this pattern of pixels that we want to plot to the screen. So when we load that into the A register, that will be the value that we need to store into the display memory, which is what we're doing in our third line right here. Load brackets HL comma A, and HL, of course, we just preloaded with the value of location in the display memory. And so now we're going to load this value in the A register, which represents our pattern of pixels that we want to plot. So now we're going to load that value that's in the A register into the display memory, and that should get plotted to the screen. And that's what happened automatically when we did that in the ZX Spin emulator. But let's see what happens when we do it in the C-Spect emulator using this program now. So I'm just going to save this program. And if you're not already familiar with setting up the environment for creating these assembly language programs for doing development for the ZX Spectrum Next, and if you don't already have your own development system set up, then if you like, you can go back and watch the video that I made on how my development environment is set up. So I'm just going to go and execute a batch file now, which will automatically assemble this program and run it in the C-Spect emulator. I think what I'll do is I'm going to do it in two parts. So normally I just execute one batch file that automatically assembles the program and runs it in the C-Spect emulator, but this time I'm going to do it in two parts. So the first thing I'm going to do is run a program or a batch file which will simply assemble the program and create a .nex file. So my batch file is named M, so I'm just going to execute. Let me just zoom in here so we can see what we're doing. There we go. So I'm just going to first of all execute a batch file that's called M, like this. And you can see here it's assembled our program, And according to our template program in my development environment that is set up here, you can see by this line of text here that says save next open project.nex. This is going to tell the sjasm plus assembler, which is what I'm using in my environment, to automatically create this .nex file, which is what we're going to be executing in our CSpec emulator. So now, since I've just assembled this program using my batch file, I'm going to go back to my command window right here, and now I'm going to execute another batch file which will run that .nex file through the CSpec emulator. And that batch file is called R. And so let's see what happens when I run that. And here you go. Here's the CSpec emulator running now. And you can see that it's not displaying anything on the screen. There's no pixels being displayed here. There should be that pattern of pixels that we saved into the display memory, but it's not showing up. And it turns out that the reason this happens is because apparently when you load a .nex file into the CSpec emulator and run it, and maybe this happens on an actual Spectrum Next as well, I assume it does, but apparently what happens is when this program gets loaded, the entire display memory as well as the attribute memory gets automatically filled with a value of FF. So if all of those bytes are filled with a value of FF, then the display memory will be filled with pixels, so all of the pixels will be turned on. And if you're wondering, well, why aren't all the pixels turned on and the screen is completely white? Well, that's because the display memory is also filled with the value of FF. And if we look at our attribute values right here, we can see that a value of FF would mean all of these attribute pixels are turned on. So that means if we start, let's say from the left side here, this flashing attribute would be turned on, and the brightness attribute would be turned on, and then the paper would have a value of 111 in binary, which is 7 in decimal, and 7, of course, is the color value for white, and then the ink value would also be 111, which is decimal 7, which would also be white. So apparently by default, when you load a .nex file into the CSpec emulator, the display attribute is filled with FF values, which means every display attribute location will have white ink on white paper, which is bright and flashing. And if we go back to our emulator here, we don't see anything flashing because it's white paper on white ink, so we won't see that flashing anyway. So what we need to do in order to actually see something on the screen is to change the values of both the display memory and the attribute memory. Ideally, we want to clear those out to have the display memory all filled with 0, so that would be no pixels showing on the screen. And the attribute memory, we want to fill that with a value that would have a certain ink and paper color that we determine, like for example, black ink on white paper. So here you can see that there's nothing displaying on the screen, but in reality the entire screen is filled with pixels, but those pixels are white ink on white paper, flashing and bright. However, our program did plot our pattern to the screen, or it should have plotted our pattern to the screen, but we can't see it because it's in white ink and white paper. So let's go back to our program now and see if we can just change the attribute value of the character location where our pixels should be plotted, and we'll see if they'll show up. So I'll just exit out of the emulator here, and I'll go back to my program, and let's take a look at our program again right here. So here, just to quickly review, we're loading a value of 4000 into the HL register pair, which is the top left corner of the display screen. And then we load our byte value in there to give us our pattern that we want to plot into the A register. And then we save that A register value, or that pixel pattern, into the display memory. So this code should be actually plotting our pixel pattern to the screen, but we just can't see it because it's in white ink on white paper. So why don't we modify our program a little bit here, first of all, to change the attributes of the top left-hand character position on the screen to make it, let's say, blue ink on yellow paper. So what I'm going to do now is load a value into the HL register pair again. And this value is going to be the address of the start of the attribute memory, which is 5800 hexadecimal. Just like that. And I'll put a note start of attribute memory. Okay, and now we want to load a value into the A register, that represents the colors that we want that character square to have. So what did I say we wanted to have? Blue ink on yellow paper. So blue ink would be a value of 1. The ink value would be 1. And the paper value gets multiplied by 8. So yellow is the value 6. So if we multiply 6 by 8, that gives us 48. And then we add 1 to that, that's 49. So that should give us an attribute of blue ink on yellow paper. So I'll enter 49 here. And this will be blue ink on yellow paper. All right, and now we just need to simply load this attribute value to the memory location that corresponds to the first byte of attribute memory, which we've already loaded into the HL register pair. So I simply have to enter load HLA or load brackets HLA. Just like that. And I'll just put a note set attribute value. There, so now this program, although it was already plotting our pattern to the screen, we couldn't see it, but now it's also going to be changing the attributes of that character location where our pattern gets plotted. Now, before I run this program, I just want to give you a bit of a mini challenge to try and guess what do you think we should expect to see on the display given everything that we've discussed so far in the video. And so it might not be obvious, or it might be obvious, I don't know. It wasn't obvious to me, but maybe it's obvious to you. So let's go ahead and save this program. And I'll go ahead and run it again, and we'll see what shows up on the screen this time. And this time I'm just going to run it using the regular batch file to automatically assemble and execute it in one step. And there we go. So was that what you were expecting to see? And if it wasn't, can you think of why it's displaying this instead of what you were expecting to see? So if you were expecting to see just the pattern of pixels show up with those 4 pixels, remember that I mentioned that by default, the entire display memory gets filled with the value of FF, which means every pixel on the display is turned on. So even though we're modifying the pattern of just the first line of the first character, the rest of the screen is still filled with pixels, we just can't see them. But of course now we can see them in that first character square because I've changed the attribute values to blue ink on yellow paper. So now let's go back to our program and see how we can go about clearing out the display memory and setting the attribute memory all in one go before we even try to plot anything to the screen. So I'll go back to my program right here. And now let's go through the rest of this program. So I'm going to reactivate the top 2 subroutines by taking out these semicolons, which has turned them into comments. So now they're no longer comments, they're active in our program. They're actually going to do something useful for us. Just going to line up these comments because that bugs me. All right, so now we have 3 subroutines that are going to execute this time. And we already know what subroutine 3 does. That plots the pixels to the screen for us. But now, before I continue, I want to just disable those extra lines of code that I added to change the attributes of the top left corner character position of the screen, because I won't need that anymore, because now I'm going to be setting the attributes for the entire screen all in one go. So let me go down here and I'll just comment out these lines. There, so those lines are now commented, they're no longer active. Now let's take a look at the rest of the program and see how we clear out the display memory as well as the attribute memory. So first our program calls subroutine 1, which is labeled sub1, which is right here, sub1, and it says set attribute values of entire ULA screen. So first we want to set the attribute values of the entire screen to set our own paper and ink colors. And let's see what value we want to choose. So here in our first line, I'm loading a value into the A register, and the value that I've chosen is 56. And can you figure out what value 56 will give us in terms of colors? Well, since the paper color gets multiplied by 8, this would give us a paper value of 7. So 7 multiplied by 8 is 56. So we have a paper value of 7, which is white paper. And then we're adding actually an ink color of 0. So I can just put that here, plus 0. So it's going to be an ink color of 0, which is black. So in this case, we're going to have black ink on white paper, and maybe we'll just change it up a bit. Why don't we have red ink on white paper? So I'll change this comment to red. And then instead of adding 0 to our white paper, I'll add 2 because 2 is the value for the color red. And now we are ready with our attribute value loaded into the A register. And since I'm not adding any extra values for flashing or brightness, then this square should not be flashing or bright. Actually, maybe we should make it flashing and bright. Do you want to do that? Okay, why don't we do that right now? So if we go back to our attribute values, right here, flashing is bit number 7, which has a value of 128. And then brightness is bit number 6, which has a value of 64. So let's go back to our program, and we will add 128 for the flashing, plus 64, plus 56, plus 2. So now we should have the entire screen. Oh, actually the entire screen is going to be flashing. Okay, well, so the entire screen is going to be flashing, and it's going to be bright, and it's going to have white paper with red ink. Okay, that's going to look kind of startling, but oh well. We can always change it, right? Okay, so what do we do next? So now we're going to use an instruction that I haven't covered before in my tutorial series. I keep calling it a tutorial series. It's not supposed to be a tutorial series. It's just me documenting my programming journey or my game development journey, but it's kind of a tutorial, I guess. So what I'm doing next here is we're going to be taking a look at this instruction here, LDIR. So if you're not already familiar with LDIR, you might want to become familiar with it and pay attention to this part because it's a really useful instruction. And essentially how it works is it automatically copies large sections or small sections. It automatically copies data from one memory location to another. And if we take a look at Z80 Heaven here, and I'll just bring the screen over here, right here. So here's the LDIR instruction here. Let's take a look at it and see what it does. So right here is where it describes what the LDIR instruction does. And you can see here it says, first of all, repeats LDI. So LDI is actually the majority of what this instruction does is it performs the function that LDI performs, which I'll explain in a moment. But the instruction that we're going to be using is actually this one here, LDIR, which essentially what it does is it performs the LDI instruction, but it repeats automatically. So here let's take a look at what it does. This is the first instruction that it does. So what we're going to do is load up the HL register pair with a value that represents a memory location. And then this instruction is going to extract whatever byte of data is stored in that memory location, and it's going to put it into the memory location that's pointed to by the DE register pair. And then it increments the DE register pair as well as the HL register pair. So both of these memory addresses will get incremented, as well as the BC register pair will get decremented. So it's using BC as a counter. So essentially what we want to do here is think about exactly the process we're trying to achieve. We have a bunch of memory locations that we want to set with a particular value. In this case, it's the memory locations that correspond to the attribute memory. And so what we're going to do is set HL to the memory location that corresponds to the first byte of data in the attribute memory. And we're going to set DE to a memory location that corresponds to the second byte of data in the attribute memory. And then we're going to preload a value into the first memory location. So whatever value we load into that location, that's the value that we want our entire attribute memory to end up containing when we're all done. And so this program or this instruction is going to do exactly that by incrementing both HL and DE values, which is going to increment both of those memory locations. And it's going to use the BC register pair as a counter. So let's see how we do that. And here we go. So first of all, you can see I'm loading a value into the A register that represents the attribute value that I want, which we just looked at. And now we're loading a value into the HL register pair, which is 5800 hexadecimal, which corresponds to the first address of the attribute memory. And so this is the address we're going to preload with our byte of data that represents the color attributes that we want. And we'll do that right now. So in this next line here, it says load brackets HL, and I'm going to change this 56 actually to A, just like that. So now that color attribute value that we loaded into the A register, we're going to store that into the memory location pointed to by the HL register pair, which we now know is the first memory location that stores the attributes for the computer screen. And we're going to load the DE register pair with the second memory location of the attribute memory, which is 5801 hexadecimal. And then we need a counter to tell the computer how many times we want to copy this value throughout the entire screen. And there are actually 768 character locations on the screen. But since we're already preloading that first location with a value right here, we don't need to have our loop counter count that one. So we're going to set our loop counter, which is the BC register pair, to 767, which is one less than the number of character locations on the screen. So now if we take a look at this program, just so we understand what it's going to do, we're loading HL with a value of the first memory attribute location. We're loading DE with a value of the second memory attribute location. And then we're loading BC with a counter of how many times we want to copy the value of the first location into the second location. And then it's just going to cycle through and it's going to increment the HL and DE memory address pointers, and it's going to decrement the BC counter, and then it's just going to copy that first byte that we loaded into essentially every address for the entire screen attributes. So that is what sub 1 should do for us. And maybe we should try the program just with sub 1 by itself to see what happens. So I'll go back up here and I'll comment out sub 3 like that. And let's save it now and we'll run it. And now we would expect the entire screen to be filled with pixels except for that top left hand line that we're plotting to the screen. And now the entire screen should be flashing and bright and just look horrible, but let's see what happens. And there we go. It's flashing and bright and horrible. And why don't we have any pixels on the screen here? We should have our pattern of pixels on the top left of the screen, right? Why are we not getting that? Let's take a look. Oh, because I commented out the wrong subroutine. Okay, so now I need subroutine 3, which is going to plot our pixels to the screen. And subroutine 2 I don't need. So let's save this again. And now this time when I run it, we should expect to see our pattern on the screen with all that flashing. Actually, why don't we just turn off the flashing? That's kind of annoying. So I'm going to just remove this 128 for our flash attribute. Just going to delete that. So now we just have brightness turned on with white paper and red ink. So let's save this and run it. And there now we have our pattern showing up on the top left corner of the screen in red ink on white paper. But remember, the entire rest of the display memory is still filled with pixels. So now we have to go clear out those pixels. So how do we do that? Well, as you can probably guess, we're going to do it exactly the same way. In sub 2 here, we're going to again use the LDIR instruction, which will copy bytes of data from one memory address to another memory address and then increment both of those addresses and keep repeating that until all of our addresses are filled with this byte of data. So let's see what values we're going to use this time. So here I'm loading a value of 0 into the A register because 0 will turn off all of the pixels. This time I'm using a value to represent a pixel pattern, and I want the pattern to be empty. I want all of the pixels to be turned off. So I'm using a value of 0. And then I'm loading the HL register pair with the value of 4000 hexadecimal, which is the start of the display memory this time. Remember, we did the attribute memory value last time. This time we're going to be loading a value into the display memory, and the display memory starts at address 4000 hexadecimal. So I'm loading that into the HL register pair, and then we're going to load that address with our value that I put in A, which is 0. So we're going to turn off all the pixels in the first display memory address. And then here I've got my DE register pair. I'm loading up with the second address, which is 4001. And then we have our BC register pair being loaded up with a counter, which is one less than the number of display bytes on the screen, which is 6144. So this is being loaded with 6143, which is one less than the total number of display bytes that get displayed on the screen. And here's our LDIR instruction right here. So this section of code should fill the entire display memory with a value of 0. So now let's go ahead and re-enable this subroutine as well, right here. So now all of our subroutines are enabled, and we should be, first of all, calling sub1, which sets the attribute values for the entire screen, and in this case we're setting it to red ink on white paper. And then it calls sub2, which clears the entire display memory, so it sets it to a value of 0, so all of the pixels should be off this time, giving us a completely white screen. And then we're going to be calling subroutine sub3 here, which is going to plot our pattern of pixels to the screen in the top left corner. So let's go ahead and save our program, and then we'll run it through the assembler and our C-Spect emulator. And now we should expect to have a white screen because we've turned off all the pixels. We've preloaded the entire display memory with zeros, and we should have a single pattern of pixels in the top left corner, red ink on white paper. So let's give it a shot and see if it works. Success. Exactly what we expected. So now the entire display memory is cleared. The entire attribute memory is not cleared, but remember we loaded it with a value that equates to red ink on white paper, not flashing, but bright. So now we can easily go back and modify the program. So now what would happen if we went back to our program here? And remember we loaded a value of 0 into the display memory, and we filled the entire display memory with 0, which means all the pixels are turned off. But what if we loaded this with a different value? Let's say we loaded it with a value of 1. What would happen then? Can you guess what we would expect to see now? Well, now we're loading every display memory with a value of 1. And 1, of course, is a single pixel turned on. So every single line or byte of display address memory should have a value of 1. And let's see what we get. Let's save it and run it. And there we go. Since every byte now has a value of 1, we get this stripe pattern on the screen because every single location is going to have the same single pixel turned on in every line. So there's an introduction to how we can use the ULA display memory on the ZX Spectrum Next. And we looked at how we can clear out the display memory and preload the attribute memory. Because of this particular feature of the ZX Spectrum Next, when it loads a .nex file, it seems to load these FF values into both the display and attribute memory. So we need to clear those out and set them to the values we want before we start plotting pixels and colors to the screen. So I'm sure there's more complicated and advanced methods of using the ULA memory on the ZX Spectrum Next, but this is what I've learned so far, and I wanted to share it with you, and hopefully it's been interesting and useful for you. And I want to thank you for watching, and thanks for joining me on this journey, and we'll see you in the next video.